Calculus free response question number 4, part C from the 2012 released calculus free response questions. Now, this is the difficult one. It says we have this other function g. Now, this function isn't defined by an integral like it was in our previous problem. It's defined as a piecewise function. So this square root 25 minus x squared that they're so interested in, that's part of the function. And the other part is just this linear function x plus 7. And we want to be thinking of a graph of this function that f of x behaves a certain way from -5 to -3. And then at -3, see, this is going to be the interesting point, is the -3, because it jumps from one function to the other. And the question is, does it jump in such a way that it's still continuous or not? In other words, did we make a big jump, or did we really just keep going along the same line? That's our question here. Is g continuous at x equals -3? And I need to use the definition of continuity to explain my answer, so I hope I know what that definition is. So we'll start by really thinking about this function f of x. So here's our f of x function. It's square root 25x squared. Now, I might not know a whole lot about this function. By the way, you will find it useful because this type of function comes up a lot in the AP exam. If you can recognize this as a semicircle, that's what it is. This is a semicircle radius 5. This is the upper half of a circle with radius 5. But you don't have to know that to answer that question. If you do know it, it's helpful. But not really all that much. I think what we do want to be aware of this function f of x is that when x does equal -5, if I plug the -5 into the x squared, I get 0. So this f of x starts at 0, and then as the -5 moves toward the 0, the x squared is decreasing, so it's going to be an increasing function. So these are some things we can get about square root 25 minus x squared, even if we don't know much about it. And then this x plus 7 is a linear function. So with that information in mind, we can sort of sketch this out. Now, the sketch, we aren't going to get any kind of points or reward for that, but it might help us to lay out what the problem looks like. So if I just look at the part of the x-axis that I'm interested in here, from -5 to 5, and I'm really interested in that break point at -3. So I know that that f of x started at x equals 0, and then it increases to some point which I don't know where, and I don't really know what that looks like. I know it's a semicircle, but I wouldn't have to know that. All I know is it's some function that increases, and when it gets to the -3, we stop following that function, and since the x is equal to -3, that means we have a closed circle on this function. Now, the x plus 7 is a linear function, and if we put in the y-axis, which is going to be about here, so here's our y-axis. What we're really interested in is, if I have this linear function, and I know its y-intercept is 7, because the graph is y equals x plus 7. So I know that its y-intercept is 7. And I know its slope is 1. So the slope 1, that looks like this. Now, my question is, when it comes down to here, does it catch right on to this point, or is it a little low, or is it a little high? That's what I have to know, and I want to know that rather precisely. So what I can do when I look at a piecewise function like this is, if I want to know what's happening at x equals -3, because that's the point we're interested in, at x equals -3, I can evaluate the function at x equals -3 because it's equal to f of x when x is equal to -3. So I can just take that -3 and put it into my function. So at -3, this part of the function is equal to square root of 25 minus -3 squared. Now, we already figured out in the previous problem that this is 4. And if you're concerned about being 4, you can work that out, and you can use even your calculator even, because it's a calculator active question. Now, the trick we're going to pull to understand if these two meet or not is that if we look at the lower part of the function, because the -3 is excluded from the domain of this part of the function, we're not supposed to plug the -3 into this function. But if we go ahead and plug the -3 in anyway, what we're going to find out is where is the hole at the end of this function, because this function ends in an open hole. So it ends like this, and our only question is, where is that hole? Is it below, is it above, or is it right on? So to find out where this hole is, I go ahead and plug the -3 in, even though it's excluded from the domain. And so I say, all right, so I'm going to plug that in for the x, so that's -3 plus 7, and oh, that's also 4. Now look, as soon as I notice that these two parts of the function, their values are both 4, I already know the answer to this question. G is continuous. I can already say that. I might even get a point just for saying that. But most likely I'm going to need this in order to get all the points. So I already know that it's continuous because I have figured out that when I follow the x plus 7 curve down, the open hole that it has is at the same point as the end of this function. So this actually gloms right on there and they catch each other. And that's what we expect from a continuous function. So one thing that we can say right away is g of x is continuous at x equals -3. Now I know that from looking at the graph, but that's not going to count as a justification, especially since it said use the definition of continuity to explain your answer, and I certainly have not used the definition of continuity. For all they know, I don't even know what it is. So now, let's look at the definition of continuity. There are a couple of different ways to write the definition of continuity. My favorite one involves 3 parts. The 3 parts of the definition of continuity are, 1, that f of x exists. And this is, we should say, the definition of continuity of a function. I guess our function is g, so let me be consistent with that notation. So, well, I guess we'll still call it f here. And we'll show that these things hold for g. So function is continuous, a function f is continuous at a point x equals c. So these 3 things have to happen. F of x has to exist. Part 2 is the limit as x approaches c of f of x exists. Part 3 is that f of x that exists is equal to that limit as x approaches c of f of x that also exists. Now, many people, by the way, just write this part and say that is the definition of continuity. That is, in fact, an adequate definition of continuity, because if I write that these 2 things are equal, it implies that they both exist. But I like separating it out like this because it allows us to entertain separately the question that these 2 things exist, and it makes that implicit existence explicit. Now, so let's go and check these things for our function g. So for g of x at x equals -3, g of -3 is equal to, well, what's g of -3? So if we go back to our definition, g of x, if x is equal to -3, g of x is just equal to f of x. Therefore, g of -3 is equal to f of -3, and f of -3 is equal to the square root of 25 minus -3 squared. We keep coming back to this, and it's still 4. All right, so we've now established that g of -3 exists. Not only that it exists, but also that it's 4. Now, when we go to look at part 2, the limit of f of x exists. Now, when we look at the limit of this function here, and we want to show that the limit as x approaches -3 exists, there's really 2 parts to that. We need to show that the limit as x approaches -3 from the left exists, and that the limit as x approaches -3 from the right exists, and that they are equal. So because this is a piecewise function that breaks at this point, there's a different function from the left and from the right. Well, if we can show if those 2 limits from the left and the right are equal, then we've shown that this limit is equal, and then we've shown that this limit exists for part 2. So we have to look at the limit from the 2 sides. And in fact, so what really happens in terms of the limit definition is that this part 2, the limit as x approaches c of f of x exists, that breaks out into 3 separate parts, which are that the limit as x approaches c from the left of f of x exists, the limit from as x approaches c from the right of f of x exists, and that those 2 limits are equal. So the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x. And again, a lot of people will just write this third one, but I like to break this out and say this implies that both of these limits exist and they're equal to each other. So now let's go about showing that those two limits exist. So now this was really our part 1 there, and our part 2 is we're going to say, what is the limit as x approaches c from the left? So we want to know what is the limit as x approaches -3 from the left of g of x, our function that we're interested in. Now, if we are approaching -3 from the left, that means our x value is less than -3. If our x value is less than or equal to -3, we're going to use f of x for our function. If it were more than -3, we would use x plus 7. But as g approaches -3 from the left, that's coming from this side, our x's are less than -3. So we're going to use the part of the function for x is less than -3, which is f of x, which is our old friend up here. So the limit as x approaches -3 from the left of g of x is equal to the limit as x approaches -3 from the left of f of x, because these two functions are the same thing when x is less than -3, which this negative means. Now, when we write this equation, we don't want to drop that limit sign. We're interested in the limit. We don't want to say g of x is equal to f of x and start dropping the limit sign. This limit is equal to this limit, and that is the limit as x approaches -3 from the left of our f of x. Our f of x was square root of 25 minus x squared. Now we want to go and evaluate this limit. So to evaluate this limit, the first thing we should do is say, can we evaluate this limit by substitution? And the question is, could I take this -3 and just plug it in for x squared, and would it be defined? So the only way that this square root would be undefined is if when I plug in the -3, I get a negative number. But we can see I'm not going to get a negative number. So I'm now going to evaluate this limit by substitution. And what that means is that I can now drop the limit sign and plug the -3 in. So this is equal to square root of 25 minus -3 squared. And then we have already concluded that that's 4. In fact, everything's coming up 4 here. All right, so this is the first part of part 2. I've shown that the limit as x approaches -3 from the left exists and is 4. Now I need to see about the limit as x approaches -3 from the right of g of x. Well, if I'm approaching -3 from the right, then I'm up here approaching from the right, and my x values that I'm using are greater than -3. So if my x values are greater than -3, then I need to be using x plus 7 for my function. So now I can say that my limit as x approaches -3 from the right of g of x is equal to the limit as x approaches -3 from the right of x plus 7. So again, what I've done is just replace the g of x with a value from the definition of g of x that allows me to compute things. Now I can look at this and say, again, could I just take the -3 and plug it in for the x? Is there a hole in the function? Is there an undefined? Is there infinite discontinuity? Well, no, there's nothing. I can do -3 plus 7. You learned that in pre-algebra, and there's no problem with doing it. So that means that, again, I can evaluate this limit by substitution. And that just means I'm going to replace the x with the -3. When I do that evaluation of the limit by substitution, the limit sign drops. When I do this evaluation of the limit by substitution, the limit sign drops. Now I just have -3 plus 7, and that equals 4. So now what we've done is we've established that the limit from the left at a -3 exists and equals 4. The limit from the right at -3 exists and equals 4. So in fact, I've shown that this limit exists, that this limit exists, and that the two limits are equal. So I probably need to write out this last step. I got 4 for both of these, so I can say, since the limit as x approaches -3 from the left of g of x is equal to the limit as x approaches -3 from the right of g of x, it follows that the limit, and they're both equal to 4. It follows that the limit as x approaches -3, let's rewrite that, the limit as x approaches -3. And this time I'm not saying from the left or right, because I've established the limit from the left, the limit from the right, they're both 4. So I'm now ready to say the limit overall of g of x exists n equals 4. So now I've established part 2, that the limit as x approaches c of f of x exists. I've established that it exists, n equals 4, and I know what f of x is, it's also 4. Everything's coming up for us. The f of x exists, it's 4, the limit exists, it's 4, therefore f of x equals limit as x approaches c of f of x. So my final conclusion is, since limit as x approaches -3 of g of x is equal to g of -3, and they're both equal to 4, it follows that g of x is continuous at x equals -3. And now I've answered my final question. I've done a lot of work here, so let's go back and make sure I answered it all. All they asked is G continuous? Did I answer that? Yes, right there. G of x is continuous at x equals -3. I didn't need all this work to answer it. I just needed to understand the graph. Then, use the definition of continuity. Did I use the definition of continuity? I used it right here. Now, all you have to write is this part. You don't have to write the words definition of continuity. You can if you want. You also don't really have to write these two. You just need to make sure you write that one. And to explain my answer. Did I explain my answer? That really comes down here, and this is my final conclusion regarding all my exploration of the definition of the limit of continuity, is that since the limit as x approaches -3 is equal to the value at -3, it follows that g of x is continuous at x equals -3. So now I've answered all the parts of part C.